In the second half of 8.7, which I'm calling 8.7b, we are going to be solving exponential equations. So you'll notice exponential equations have a lot of the same properties as the logs. This first one is the exact same property we just did with logs at the bottom of the last page. If the bases are the same, equate the exponents, where with the logs it was if the bases are the same, equate the arguments. With exponents, if the bases are the same, equate the exponents to solve. So as an example, you could show 3 to the x plus 2 equals 3 to the fourth, for instance. If the bases are the same, yes they are, I can solve this equation by equating the exponents. X plus 2 equals 4. Subtract 2 from both sides. X is 2. So that's what the one-to-one exponent property is, or the equivalence of exponents. If the bases can be made the same, then you can do this. The problem with this, very few bases can be made the same. Most of the time, like one base is 5 and one's 7. You can't make them the same. But for the ones that you can, it's a nice, easy rule, because you're going to see the second type that we're learning where you can't make the bases the same, a lot more work. So I look at this problem and go, could I make these bases the same? So 3 can't be broke down, but could I break 27 down into 3 to the something? Absolutely. 3 to the third. Remember when I told you to remember those perfect squares and cubes when we were doing radicals? How many times have I went back to that and said, oh, if you remember your cubes, oh, if you remember your squares. So that's why I said you should memorize those by sight, because they just keep coming back. So you should know when you see 27 that it's 3 cubed. Well, if this is 3 to the x plus 8, and I can rewrite 27 as 3 cubed, do you see a direct application of the one-to-one exponent rule? If the bases are the same, solve by equating the exponents. X plus 8 equals 3 minus 8 minus 8, x equals negative 5. And guess what the best news is? There's no log in the equation, so I don't have to check it. Woohoo! So, is it a good idea to check it? Oh, absolutely. It's always good to check anything that says solve. So put negative 5 in. Negative 5 plus 8 is 3. Is 3 cubed 27? Ding, ding, ding. Yes, it is. So negative 5 is our solution. But do they have to be checked? No. So if you're running out of time on a test, you have to check the logs. But the exponentials, good idea to check. But if you don't have time, they don't pick up extraneous solutions like the logs do. Okay, now this one's a little trickier, so watch this method because it's going to come in handy later. So I see 2, base of 2. I know I can't break that down, so I say in my head, can I break 8 down using 2? Oh, another one from your cube table. Yes, 8 is 2 cubed. So I could rewrite this as 1 over 2 cubed. Because remember, my goal is to make the bases the same. Students go, how did you know to turn that into 2 cubed? Well, I looked here for 2, and I say to myself, can I write 8 as 2 to the something? Yes, 2 cubed. So it wasn't just a mystery that I picked it. It was because of this one. So here's my new problem. But, sorry, that turned out bad. But the problem is, this is a base of 1/2, and this is a base of 2. Well, we learned in chapter 4, here come the exponents back. If you change sides of the fraction, your exponent just changes signs. So couldn't you write this? So if it's 2 cubed in the denominator, when we bring it up, it's 2 to the negative 3 times x is negative 3x. So bringing it up changes the sign of the exponent, 2 to the negative 3, then we multiply it by x, and we get negative 3x. So think of it like this, if that's like too much for you to do in your head. That turns into 2 to the negative 3. Then you still have your x there, and the exponent rules say to multiply negative 3 times x, negative 3x. Now look at this. Woohoo! My bases are the same. So now I can equate my exponents and solve. So subtract 1x. I need all my x's on the left. So I get negative 4x equals negative 4. So divide both sides by negative 4, and it's looking like we have x equals 1. And again, you can easily check it. Put 1 in. 1/8 to the first is 1/8. Put 1 in. 2 to the negative 3 is 1/8. Boom. Visual check takes 10 seconds. Okay, so just put 1 in on both sides and make sure you get the same number. We got 1/8 on the left, we got 2 to the negative 3 on the right, but you learned in chapter 4, 2 to the negative 3 is 1 over 2 cubed, which is 1/8. Okay, so like I said, great fun little method, but it only works for very, very, very few, because most of the time this is going to be an 8 and this is going to be a 7. There's no way to make them the same number. When you can make them the same base, this is nice and quick and easy. Don't have to pick up a calculator or anything. So next we're going to learn, what do we do if we can't make the bases the same, which is probably 90% of the time. So we have to make sure one of the exponential expressions is isolated. And then look what we're doing. Voila! So we turned the logs into exponents by doing loop and swoop. We're turning the exponents into logs. So look at this tangled relationship these inverses have. So to solve a log, we use loop and swoop and change it to an exponential. To solve an exponential where the bases aren't the same, we take the log of both sides. To me, that's just like wild. So if there's an e in the problem, we'll do the natural log of both sides. If there's no e, then we usually do log base 10. Then here comes one of those properties again from 8.4. Once you've taken the log of both sides, then you use the power rule to bring the power down in front, and then you solve what's left. Again, there is no log in the original problem, so these don't necessarily need to be checked, but that doesn't mean you shouldn't check. I always check. If it's, a quick, fast one like this one, you're going to see the answer is really crazy, so it would be hard to check. But if it's an easy answer, I do check it. So look at this problem. 2 and 3. I can't break either number down, and I can't make them have the same base, right? Now, if this was 3 and this was 9, yeah, I could make them have the same base. Or if this was 2 and this was 8, yeah, and not 2 and 3. So according to the directions above, if you can't make the bases the same, you take the log of both sides as long as the exponential is isolated. So is my exponential isolated? Yes, it is. It's all by itself on the left side. So now I take the log of both sides, and you can either do natural log or log, it doesn't matter. So take the log of both sides means you add the word log in front of that, and you add the word log in front of that. So you're probably going, how can you do that? Well, the rule with equations is as long as you do it to both sides, it's okay. So you'd add the log in front of this one, you add the log in front of that one, still balanced. So we haven't changed it. This is usually where students get stuck on this one. Right after you take the log of both sides, you have to do the power rule like it showed above. If there's a power there, you bring it down and multiply by the front. And I have a power there, so I have to bring that whole thing down because it is a quantity. It needs to be in parentheses. So this turns into x plus 8 times the natural log of 2 equals the natural log of 3. So keep in mind what solve means. Solve means get x alone. Solve for x. So at this point I can go, oh, well, this is times. I can divide both sides by natural log of 2 and start working on getting that x alone. So when I divide both sides by natural log of 2, I get x plus 8 equals natural log of 3 divided by natural log of 2. One more step to get x alone. Subtract 8, subtract 8. So x equals natural log of 3 divided by natural log of 2 minus 8. And remember, if the problem does not say round, don't touch your calculator. That means they want an exact answer, and your exact answer is natural log of 3 divided by natural log of 2 minus 8. So that's what you write when it just says solve. It says nothing about rounding, so don't round unless asked. And you'll see on the next page, one asks you to round, one just says solve. One asks you to round, then one just says solve. So you have to read the directions carefully so you know whether to type that into your calculator. This one did not ask us to, so that's how we write the solution. Okay, I think we might have time to do one problem on the back before we run out. Okay, so step one, if you can't make the bases the same, I can't make E and 7 the same. E is like 2.71, blah, 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 blah. And I can't make that equal to 7. So if I can't make the bases the same, then I take the log of both sides. And in the directions, I said, if there's an E in the problem, take the natural log of both sides. So natural log E to the 2x equals natural log 7. And the natural log does have to be written first because these become its argument. So don't put it afterwards. That doesn't make sense. You can't have a natural log without an argument. So you put it in front of each term. Everything I've done is valid because I did the same thing to both sides. So let's see. Are you thinking of anything from past sections? Think about the rules we learned in 8.4. When the base of the log is the same as the base of the exponent, they undo each other, and the answer is just the exponent. And that's why I said always use natural log when you see an E, because you're going to have that nice nifty little thing happen there. So natural log's base is E. The exponent's base is E. They undo each other, and we learned in 6.4 that means the answer is the exponent. So my next step is this, and I am almost done. Love these problems. So keep in sight what solve means. Solve means get x alone. So I have one more step to get x alone. Divide by 2. Divide by 2. Boom. I am done. Natural log of 7 divided by 2. I look up in the directions and see if they want me to round. No, they want an exact answer. So my exact answer is natural log of 7 divided by 2. If they had asked me to round, then I pick up my calculator and I type it in the calculator. Okay, we just have 10 seconds left, so I'll stop there and we'll pick up on the last 3 problems in the next video. Bye.